In this video, we're going to talk about polynomial functions and models. There's a good chance that you already know what a polynomial function is. So, in mathematics, poly means many, and nomial essentially means terms, so many terms. This is the formal definition. You do not need to memorize that or even really understand what it means. So, it's really a sum of monomials. So, mono means one, nomials, terms. Something that's important is the degree of a polynomial function. So that is the highest power contained in that function. Please be careful and don't just assume that the first term and its power or exponent is the degree or the highest power. Sometimes it's not written in descending exponential power order. So, for example, the zero function, the constant function, where it's just f of x equal to a number, that's not zero. A linear function, y equals mx plus b. A quadratic, a cubic, a quartic, etc. Those are all polynomials. All right, let's just see if we can identify polynomial functions and non-polynomial functions. And for those that are polynomials, let's find the degree. So for A, we have f of x is equal to 2 minus 3x to the fourth. 2 is fine, that's a constant. We've got a minus and a something to the fourth power. This is a polynomial, and this is x to the 0 power, which is 1, and x to the fourth power. So the degree is going to be 4. So B is g of x is equal to the square root of x. So the x part is fine, but the square root of x can be rewritten as x to the 1/2 power. And the thing about a polynomial is that the exponent has to be a non-negative integer. 1/2, positive, but not an integer, which is a positive or negative whole number. So, not a polynomial. And here we have h of x is equal to x squared minus 2 all over x cubed minus 1. Now, we've got x squared minus 2. If that was the only part of the function, that'd be a polynomial. Same with x cubed minus 1. But put them together over a fraction. Nope, not a polynomial. Part D, f of x is equal to 0. I don't see a problem with that. It's just x to the 0 power, which is 0 times 1. It's really, really straight, a really horizontal function at the x-axis. So that's a polynomial. Same thing is true for g of x is equal to 8. If it's just equal to a constant, that's a polynomial. So that means that they both have a degree of 0. It's like writing x to the 0 power right next to it. And our last one here is h of x is equal to negative 2x cubed times the quantity of x minus 1, all squared. So, although this would require foiling to get it into something that looked like this, where all the terms were being added together and not multiplied, in its current state, or if I foiled it and multiplied and distributed and all that good stuff, that's still a polynomial. It's got non-negative integer degrees or exponents. It's not in a fraction. It's looking good. And so for the degree of that function, I know that if I FOILed this out, the highest power here would be 2. And if I distributed the x cubed to that x squared, I know that I would need to add the exponent. So 3 plus 2 is 5. So the degree of this function would be 5. Two important features of graphs of polynomial functions are that those graphs are smooth and continuous. So smooth graphs have no sharp corners or cusps. So a corner looks like that, a cusp looks like that. It's essentially like a weird point. And they are continuous, which means that it has no gaps or holes that can be drawn without lifting your pencil from the paper. So there's a gap here, there's a hole there. An asymptote would also not be continuous. So this graph over here, that is a smooth and continuous polynomial function, where this is a graph, but it is not a polynomial graph. Sometimes polynomial functions are referred to as power functions of a degree, and you can use the variable n to represent that. So that's a monomial function where I would just have 3x or negative 5x squared, 8x cubed, negative 5x to the fourth. It has one term that has a non-negative integer exponent. More things about the graphs of polynomial functions. So these are for all polynomial functions, not just for power functions. But when we talk about real zeros, those are zeros that either cross through or bounce along the x-axis. You've probably seen x-intercepts that are imaginary. That's not what we're talking about. We're talking about real roots or real zeros. And so how we find the real zeros is we set our y, or f of x, equal to 0, much like how you did with linear and other types of functions. So how do we know if a real zero of a polynomial function crosses or bounces along the x-axis? Well, there's a pretty easy way to figure that out. It's something called multiplicity. So a real zero might have a exponent next to it. So, for example, a factor could be x plus 1 all squared or x minus 2 all cubed. So the power indicates the multiplicity. That tells you how many of those roots you have. Sometimes you have duplicates. For example, in a quadratic, normally you have one of each root. But in polynomial functions with higher degrees than 2, usually, could have multiple duplicate roots. That doesn't mean you graph them twice. It just will tell you if it's going to bounce or cross through the x-axis. So if you have a root, whether it's 0, 1, 2, whatever, and if it has a positive exponent when it is in factored form, that is an even multiplicity. Even multiplicities will touch or bounce along the x-axis. So this point right here, that's an even multiplicity because it bounces or touches, whatever description you prefer. And if your factor has an odd exponent, that is going to be an odd multiplicity. Odd multiplicities cross through the x-axis. So that point, and that point all have odd multiplicities. It's not always super easy just from the graph to know if the power is 2 or 4 or 6, for example. So you got to pay attention to the degree of the function to figure out what the power could be. We normally assume that it's the lowest power. So for example, if it bounces, we assume it's probably 2 instead of like 22. Same for an odd crossing through. We might assume that it's 1 or 3 instead of like 43. All right, let's work through this example. Let's find a polynomial function from its zeros. So let's write a polynomial function of a degree 3, that means 3 total zeros or 3 total factors, whose zeros are -3, 2, and 5. So although this isn't a formal definition, it's what my brain thinks of when I go to write a polynomial function in factored form using the zeros and the degree. So we're going to write it in factored form, so it's going to have some parentheses, and the x's stay x, but these x1, x2, x3 become my zeros. And this a, b, and c value, those are the degrees of each zero. So here's what I have. For -3, we change the sign, so it's x plus 3. For +2, again, we change the sign. And for 5, we have x minus 5, again, changing the sign. And why we do that is that when you solve for zeros, when you solve them for quadratics, for example, you always take the factor and you set it equal to 0. So x plus 3 becomes x is equal to -3. X minus 2 becomes x minus 2 equals 0. X is equal to 2. And same deal with x minus 5. Set it equal to 0, you get x plus 5. So we always set it up like we're factoring a quadratic, so x plus or minus something, and you just change the sign of the 0 you're given. And I know a, b, and c are going to be 1 because I have 3 roots and a degree of 3. So none of these are going to be greater than 1 because 1 plus 1 plus 1 is 3. So we're good. And also keep in mind that there could be a coefficient out here. Let's just assume it's 1 just for simplicity's sake, but it could be a different number. So this is a potential answer. But if you plug in like -1/2, for example, that could also work because this is all the information we have to go from. All right, and here is the use a graphing utility to graph, yada yada. This is the graph if we inserted 1 right here, and this is the graph if we inserted -1/2. So given this information, both of these graphs plus many, many more would satisfy that descriptor. So now let's take a function and identify its zeros and those zeros' multiplicities. So our function is this long function here. It's in factored form, which makes my life so much easier. And I also graphed it, unnecessary, but it's always good to have a visual. All right, let's identify our zeros. So my first zero, or my first factor is x minus 2. Remember, we changed the sign if we set it equal to 0. So that is going to give me my first 0, which is 2, positive 2, and it has a multiplicity of 1. As you know, when there's nothing written in the exponent spot, that is 1. So it has a multiplicity of 1. So at 2, this thing should cross, and it does. So our second factor has x plus 3. Change the sign, and our 0 is negative 3, and it has a multiplicity of 2. Even multiplicities bounce or touch the x-axis, so let's find negative 3, and it does. It bounces right here. Looking good so far. And then our last factor is x minus 1/2. Change the sign. My 0 is 1/2, and it has a multiplicity of 4. So that's even. That means it's going to bounce or touch the x-axis. So here's 1/2. And because the multiplicity is high, 4 may or may not be high, depending on your experience. But it's obviously different than the negative 3, which looks like an upside down parabola piece. But when you increase the multiplicity, it kind of like pulls this function out over here. So it does cross, it just takes a long time to do it. But there's your zeros and their multiplicity. All right, so let's use what we know to graph a polynomial. So let's say I have this polynomial here. F of x is equal to x squared times x minus 2. So let's find the x and y intercepts of this thing. All right, y-intercepts, when x is equal to 0, plug in 0, get 0, because 0 squared zeroes out everything. So y-intercept goes there. X-intercept is when I set this whole thing equal to 0, so x squared is equal to 0. Technically it's plus or minus 0, but that's just 0. And then x minus 2 equal to 0 gives me 2. So y-intercept and x-intercept, and my other x-intercept. So that was kind of helpful. It only gave me 2 points on the graph. But using what we just learned, this has a power of 2. So it has a multiplicity of 2, which means it's going to bounce along the x-axis. And this factor, x is equal to 2, has a multiplicity of 1, so it's going to cross through the x-axis. Cool, but which direction is this going to go in? Like, is it going to cross this way or that way? Like, what's going to happen? Well, we have more information to work with. The degree is 2 plus 1, 2 from here, 1 from here. That makes a degree of 3. I know that's a cubic. It makes that weird swooshy swoosh thing. And I know it's positive because that x squared and that x are both positive, so it's going to create that kind of swoop. So I'm thinking this thing is going to come up here and then bounce and then come back up through the 2. Now, I would need calculus in order to figure out exactly like how far it dips down, but we don't need to do that right now because we're not in calculus. So that's my best guess. Yep. And here's what it actually looks like. And if you care, we've got the interval from negative infinity up till 0, and then you can test, oh, this is below the x-axis. That's also below the x-axis between 0 and 2, and then it gets to be above the x-axis at 2. You don't need to do this analysis, but you're welcome to do that just in case you are not sure what this thing is going to look like. Yet another piece of information that is beautiful and helpful to analyzing the graph of a polynomial function are turning points. So turning points are points on a graph where we get a local min or local max, and that results from a function going from decreasing to increasing, so that'd be a turning point, or from increasing to decreasing, that'd be a turning point. So anywhere you see a local min or max point, right? That will tell you or inform you what the highest degree of that function could be if you don't have the actual equation of the function. So, for example, this curve, you probably realize, is a quadratic power of 2. So if it has one turning point, you add 1 to find the maximum degree. So one turning point, max degree is 2. 2 turning points, maximum degree is 3. That certainly looks like a cubic. And yet another example, I've got 3 turning points here. That would result in a maximum degree of 4. Let's practice by identifying turning points and degrees of each of these polynomials. Now, do not be swayed or confused by the fact that they have identified all of the intercepts with black points. That does not mean that those black points are inherently turning points. All right, so if I'm looking at this first graph, I'm decreasing, and then I go to increase. So that means that this point is a turning point. And then as I go to increase and then I decrease, that must mean I've got another turning point. So we've got 2 turning points. That means plus 1, 2 plus 1, gives me a degree of 3. And then for this function, I am increasing, and then I change to decreasing. So there's a turning point there. So I'm decreasing, I change to increase, even though it's tiny. It still counts as a turning point. So I'm increasing, I'm increasing, and then I decrease. So yet another turning point. Kind of sneaky, but 3 turning points, add 1, that's a degree of 4. And just so you know, it does work in the reverse. So if you're given the degree, so for example, if you know that a function, a polynomial, has a degree of 4, you can subtract 1 to find the maximum number of turning points. So degree 4 would have up to 3 turning points. Degree of 3 would have up to 2 turning points, etc. They could have less turning points, but you're guaranteed a maximum of 1 less than the degree. One last new piece of information, I promise. And that is end behavior. End behavior is useful because using your first term, which has your highest degree traditionally, that's going to give you a pretty good idea of what that graph is going to look like. So for example, if your leading term was some x to the 4th, I know that my graph will look like an x to the 4th graph. If it was negative, I know it's an upside down looking W thing. So end behavior is defined as the very first term in your function, which has the highest degree. So if that means you need to FOIL or distribute to get that first term all by itself, that's what you need to do. So I couldn't let you leave without practicing end behavior. I'm sorry, have to do it. So let's find the end behavior of these 2 polynomials. Now, the way that they are written, they're in factored form. That doesn't mean I can't find the end behavior, but I definitely don't think factored form as they are is going to be helpful. So I'll show you how I find the end behavior. So what you're going to want to do is take all of the first terms. So for example, I have an x squared out here, x squared comes down. I take x, I check the power, that's x to the first, that comes down, and then I have also x to the first. So x squared times x makes x to the 4th. So this graph is going to look like a positive x to the 4th graph. That's what end behavior means. Like, where is that going to go? It's going to go to positive infinity at both ends. That's essentially what that means. So for this function, let's do the same thing. So I bring down the 2x. So if there's a coefficient in front of the variable or a negative, then you bring that down. So that's 2x to the first power times x to the second power. So 2x times x squared makes 2x cubed. So that's going to be a positive x cubed graph that's going to go to negative infinity towards negative infinity on the x-axis and positive infinity towards positive infinity on the x-axis, and it's going to be stretched horizontally by 2. So it's going to be pulled up a little bit. And just one last slide here to summarize all the steps to analyzing the graph of a polynomial function. Take a screenshot, write them down if your wrist is feeling like it. But these are all the things that we looked at. All right, cool. Thank you so much for watching.